Good afternoon, lads, and welcome to Mr. McElvara's Maths World, the way it is. Today we are talking about integral calculus, of which we have covered quite a bit already. We want to finish our unit by talking about volumes of solids of revolution. A bit of a mouthful, I know. But what it's about is this. Already in integral calculus, what we've been talking about is finding the areas under curves and straight lines. So we could easily find, in fact we wouldn't need calculus to do it, to find the area under fx here. But today what we want to do is take it one step further and calculate the volume that is produced by rotating a line or a curve around the x-axis. So what you can imagine this, boys, is this line here, which I forgot to tell you might resemble fx equals x, so y equals x in the old language. If I was to rotate that line around the x-axis and come back to the starting point, I would map out a cone, wouldn't I? A cone, okay? So you can easily do that by mapping out, by rotating a straight line around the x-axis. So that's what's going on here. We have a formula, fortunately, that helps us out to find the volume. Now, this is what you need to imagine, that when you do rotate a line around, you've got a radius, and the radius is formed between any point on the line and the x-axis. So that becomes the radius, doesn't it? And I have a circular disc that's mapped out from, say, this point here, x1, fx1. That would trace out a circular disc, wouldn't it, if I came back to the starting point. Boys, that should indicate to you that, well, the area of that circular disc is simply pi r squared, as long as I know r, the value for r, which is the height of the function, fx, I can find the area of that disc that's traced out. Now, integration is all about summing. So if I could find the sum of those area of those discs, then I'd have the volume, wouldn't I? Unfortunately, that's how it works in integral calculus. In a nutshell, what I can do is find the volume of this cone by simply summing the discs, if you like, from B to A. In this case, B would be 6, A would be 0, the origin. And so I can do that by following this template. There's pi, and there is your radius squared, and you substitute your limits in there. Okay, so that's a little bit of the theory behind it. I don't want to go much further than that. So our question might be, find the volume of the cone produced by rotating the line fx equals x about the x-axis, where x is between 0 and 6. Well, I can tell you now that you don't need calculus to solve the problem. How do we do it? By not using calculus. This is just by way of interest and background. Well, the volume of any cone is given by this formula, isn't it? The volume of a cone is equal to 1/3 area times h. Now, what's the area? Well, the area is the area of, in this case, the disc mapped out where x is equal to 6. Okay? It's the area of that circle so traced out. So, and the height, what's the height? Well, it's just from 0 to 6. Okay? So you don't need calculus. That's what I'm demonstrating here for this particular problem. So what would the area be? Well, it would be pi r squared. And r is 6 of that disc, isn't it? So pi times r squared times height, which happens to be from 0 to 6 as well, the height of the cone. Right, from the pointy end, from the vertex, to the middle of the diameter. Okay, so now you're going to find that comes to r is 6, so 6 squared is 36 times 6, 216, times 1/3 is 72, so the volume of the cone will be 72 pi units cubed. Units, U for units, U cubed. Note carefully that I've left my answer in what's called exact form. I've left pi in it. Okay? Your total volume would be about 216, a bit more than that, units cubed, but usually in calculus we are more happy with an exact answer. Okay, so don't be surprised to see pi left in the answer line. I certainly prefer to do that. How do we use integration to solve the same problem? You're about to discover that it's quicker, actually, because really, in this simple case, the volume is simply equal to pi times, well, my limits are 6 and 0 quite clearly, and all I've got to do is square the function. What's the function? Fx equals x in this case. Perhaps I should have labelled it like so. Okay, so it's the function squared, so it's just like that. And that one's easy for us to do. Alright, there's no special tricks being employed here. So the volume is equal to, let's integrate it, it's x cubed over 3. Oops, left out the pi there. Put in my limits, 6 to 0, and therefore the volume, can you see, is going to be the same as that over there. It's pi times 216 is what x cubed is, 6 cubed is, divided by 3, and units cubed, and that, as I say, comes to 72 units, I should say equals, 72 units cubed. So that's our very first example. What I'd like you to do is now have a go at this problem here, and we might press pause and take it up, do the solution in a minute.